Section 6 is numerical integration, and this is the last section for the chapter. We kind of go back to sort of a primitive looking method, but that method is the trapezoidal rule, which is a pretty powerful one actually. It's more powerful than the left and right endpoints, definitely. All right, so up until now, we've dealt exclusively with easy functions. Believe it or not, what you've been dealing with were actually elementary functions that have antiderivatives, so we can integrate very easily. Well, maybe not very easily, but easily. Anyway, we can handle that in this class using the tricks that we've learned so far. So, like pattern recognition, the substitution, that sort of thing. There's a lot of functions out there, though. Actually, there's an infinite number of functions out there that don't have situations like that we can't actually integrate in this class. Some examples that are here would be like the cube root of x times the square root of 1 minus x, the square root of x times the cosine of x divided by x, the square root of 1 minus x squared. All of the problems that we've done so far were convenient in that we could integrate them using direct substitution or something like that. Okay? None of these functions have that ability. So we can't easily use the fundamental theorem of calculus for these functions, but we can still use approximation techniques, just like we learned in the beginning of the chapter. And the better approximation technique is the trapezoidal rule. So that's what we're doing in this section. The trapezoidal rule is kind of an intuitive one once you remember what a trapezoid looks like and what the geometric formula for the area of a trapezoid is. And this one is the one that pops up on the AP exam most of the time. So it's very similar to the methods we used at the beginning of the chapter. It's just that now we're finding the area of a trapezoid instead of the area of a rectangle. Begin by labeling the example graph with 4 subintervals. So if I'm going from here to here, then I have that, and that. And notice that in each of those subintervals, my line is going directly up to the function. So the formula for area of a trapezoid, what is that geometrically? Yeah, so A equals 1/2 the height times B1 plus B2. And that's for, in geometry, you were shown trapezoids generally that look like that. And this was called the height, and base 1 and base 2. Right? Okay. Now, that's not how we're going to deal with trapezoids in this class. Because over here, if I draw that connecting line, and then I draw that connecting line, and then that connecting line, and then that connecting line, I've made my trapezoids here, 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 and here. So my trapezoid doesn't look like this. It's more like this. So how does that translate to us? Well, this distance right here is the same as that distance right there, h, right? But in calculus, what do we call that? That's our delta x. Now, this length right here is not going to be B1, and this length right here is not going to be B2. How do we find that in our class? Yep. F of xi and f of xi plus 1. Or if you called this one f of x, then this would be f of x minus f of xi minus 1. Okay. So now let's rewrite this formula in function notation. The area will be what? Okay, I'll write the 1/2 out front. I'll put the stuff inside and then the delta x at the end because that's where it usually lives in our little world. And what are we going to have to write inside? So it's not f of x, it's f of x sub I plus f of, okay, and what that says is 1/2 the height times base 1 plus base 2. All right, so here we are now. We've gone from geometry to calculus. And now to find the area under the curve from here to here, what would we have to do? Add up all the rectangles. So that means that the area equals the sum I equals 1 to, in this case, 4 of what? Now it's just the formula that's there. So the 1/2 would be here, but I can take that constant and write it out front. So 1/2 the sum from I equals 1 to, in this case, 4. But you're right, we could call that an n if you want. And then the f of x sub I plus f of x sub I plus 1 delta x. And what you're finding is the integral from 1 to 4 in this case, so from 0 to 4 of the function. So that's our notation. That's how we develop the trapezoidal rule. Now the nice thing is we can find the area under the curve. It's going to be, based on the way that I've drawn this, a fairly accurate estimate, even with only 4 rectangles. We can make it even more accurate by choosing more rectangles. Is it going to be an overestimate or an underestimate? Depends on the function. Okay? In this case, what would it be, logically? Over. Why? Oh, because of the way that I drew it? Logically speaking, right, the curve is going under my line from here to here because it's a curve and this function is concave up. Because of that, my line is above my curve the whole way through, even though I kind of haven't drawn that here. All right, so in this case, it's an overestimate, which we see visually. Okay. So here's your official trapezoidal rule. Let f be continuous on the interval from a to b. Then the trapezoidal rule for approximating the integral from a to b of the function is this mess. It looks terrible, but actually there's a couple of patterns in here, and some of this stuff we probably could have figured out on our own already. So what I want to do is just take a look at this and see if we can figure out where all this stuff comes from, because it all comes from what we've already talked about. There's no surprise here. So let's think about it for a little bit. So this part we understand, right? That's the notation that tells us what we're doing. Where could this have come from? Delta x. What is delta x when we use left endpoints and right endpoints? B minus a over the number of rectangles that we're forming. Okay, so here's b minus a over n right here. Where'd the 2 come from? Right, in the trapezoidal rule, you have the 1/2 sitting out front when you're finding the area of a trapezoid. So this is the 1/2 right here times the height, b minus a over n. So here I am, right here. That's my delta x. Sitting here, 1/2 times b minus a over n. You got it? Okay. Now, it's 1/2 times the height times b1 plus b2. So this all must be b1 plus b2 here, right? So each one of these is like b1, and then How come there's a 2 in front of that f of x sub 1? That's right. Good job. So if I draw in just a really terrible sketch here, I'll put a dot here, 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 and here. So these are the, let's say I'm trying to form that area underneath the curve, right? So I'm going to draw trapezoids. By the way, you guys are going to be doing that. Here's my trapezoids. Okay. So f of x sub 0 goes with this one right here. F of x sub 1 goes with this one right here. But then I'm going to use f of x sub 1 again when I'm trying to find the area of this one. So in reality, what I have is f of x sub 0 getting used once here only. But then f of x sub 1 gets used once for this trapezoid, and then again for this trapezoid. Now because of the fact that I'm adding up all of the, basically all the heights of the bases that I have here, so all of these lengths, really just like we did with the left endpoints and the right endpoints when we added up all of the lengths of these guys here and then multiplied times the delta x, we can do exactly the same thing here. So we add up all the lengths that we're using, but we're using this one twice. So that's why you see the 2. Now that continues all the way through for however many terms we have in here, however many rectangles we have, until we get to here. How come there's no 2 in front of that one? Again, because we're only using this one once. That's right. So the 2 ending guys only get used once. And that's why you only see f of x sub 0 and f of x sub n at the ends. Every other height here on these trapezoids that we're making, I don't want to use the word height, I guess base, every other base that we're using gets used twice. So that's why you see the 2 here, here, and then all of these terms in between will also have 2's on them. Only one here though. All of these are the bases being added together, times the 1/2 times the height. Okay? So those are the patterns you need to see. And this is what you need to remember for doing the trapezoidal rule in this section. This guy right here is where you're going to live. You want to start the problem off by writing something like this, especially if you're given a function. If you're not given a function, you're just given some data, which we'll do, then this is what you're going to want to write down. And then you'll go to here, and then you'll simplify it down and get your answer. All right, so for example, use the trapezoidal rule to approximate the integral from 0 to pi of sine x. Just an example. We want to try to use the trapezoidal rule here. Okay, so we're going from 0 to pi. So we're finding the area under the curve there. And this is a simple enough function. We could do this the normal way, but just for example. Then, compare the results for n equals 4 and n equals 8. So in the first instance, we want n equal to be equal to 4. So delta x equals we're doing delta x. So it's just divided by 4 rectangles, or 4 trapezoids. So it's just pi over 4. All that does is give me the width of each of these trapezoids that I'm making. Thank you. Definitely needed sound effects. Okay, so now we're making these trapezoids. Now this one, technically, is just a triangle, but we're still going to treat it as a trapezoid. This one is a trapezoid, this one is a trapezoid, and that one is also a trapezoid even though it looks like a triangle. Okay? We're just going to treat it like a trapezoid. So now I have the integral from 0 to pi of sine x dx equals what? Pi over 8, good. This is delta x times 1/2. Delta x is pi over 4, so we have 1/2 times pi over 4, which is pi over 8, times sine 0 plus 2 sine pi over 4 plus, okay, plus it's 3 pi over 4 plus sine pi. And all that is us saying the sine at 0 gives us the height here. The sine at pi over 4 gives us the height here. The sine at pi over 2 gives us the height here, and so on all the way through. So we have equals pi over 8 times sine 0 is sine pi over 4 is, so plus the square root of 2, good, plus sine of pi over 2 is 1, but it's times 2, so 2 plus so root 2 plus 0. Okay, so now we add all those together. We have 2 root 2's and a 2. So we have 2 plus 2 root 2 times pi over 8. Do you want it to be? This reduces. Pi times 1 plus the square root of 2 over 4. All right, what is that? 1.8961, so we'll go with 1.896 square units. Okay, that was for n equals 4. Now we want n equals 8. So I'll change colors. What is our delta x now?
So wait, don't give me the paper. You can just take the pile.
What is my delta x now?
Pi over 8.
It's pi over 8. Okay, my figure now changes. Is this going to be more accurate? Yeah. Is this an underestimate or an overestimate? Good, it's an underestimate. Was the other one an underestimate? Yeah, okay. So, let's come up with our equation now. So, the integral from 0 to pi of sine x dx equals 1/2 times delta x, so pi over 16 times sine 0 is still 0. Two sine pi over 8. We don't know that one. So what are we going to have to do? Calculator. It's not that bad. 0.765367. Okay, yeah. So what I'm going to recommend that you do, because we have all of these terms that are going to be coming up here, and you're going to be doing a lot of rounding if you start doing it one at a time, is enter all of them in at once. So we know that this is 0, but the next one is going to be plus sine, 2 sine, pi over 8, plus 2 sine pi over 4, plus 2 sine, what's the next one? 3 pi over 8, plus 2 sine pi over 2, plus 2 sine 5 pi over 8, plus 2 sine 3 pi over 4, plus 2 sine 7 pi over 8, plus 0. Because sine pi is 0. Enter all of that stuff into your calculator at one time. That way you're only rounding once. When you take the AP exam, that is what they're going to expect you to do. So be careful about that. This isn't that bad. Did you multiply by pi over 16? Okay, so this is pretty good. Good answer. This all becomes 1 point, what is it again? 97423, so 1.974. So obviously different answers, but still reasonably close. This one is supposed to be more accurate, so I'm guessing that we're pretty close to the actual answer. So let's go ahead and obtain the exact result. So that means we're going to actually integrate the function because we can. The integral of sine is what? The integral of sine is negative cosine? Because the derivative of cosine is negative sine? So it's negative cosine? Okay. So we have negative cosine x, and we're going from 0 to pi. What's cosine pi? So we have the negative out front, negative 1 minus, what's cosine 0? 1? Which is negative 2, which is 2. So what do you think? Pretty close. And notice that we didn't have to take that many trapezoids here. We're actually pretty close already with 4. We go to 8 and we're actually really close, I think. If we were to go to 16, I bet we'd be extremely close. So you get very close results very quickly with the trapezoidal rule.